Hello everybody. In this episode, I'll be speaking with Caspar Oesterheld. Caspar is a PhD student at Carnegie Mellon University, where he serves as the Assistant Director of the Foundations of Cooperative AI Lab. He researches AI safety with a particular focus on multi-agent issues. There's a transcript of this episode at axrp.net, and links to papers we discuss are available in the description. You can support the podcast at patreon.com/axrpodcast, or give me feedback about this episode at axrp.fyi. Okay, well, Caspar, welcome to AXRP.
Thanks for having me.
So today we're going to talk about two papers that you've been on. The first is Robust Program Equilibrium, where I believe you're the sole author. And the second is Characterizing Simulation-Based Program Equilibria by Emery Cooper, yourself, and Vincent Konitzer. So I think before we sort of go into the details of those papers, these both use the terms like program equilibrium, program equilibria. What does that mean?
Yeah, so this is a concept in game theory, and it's about the equilibria of a particular kind of game. So I better describe this kind of game. So imagine you start with any sort of game, sort of in the game theoretic sense, like the Prisoner's Dilemma, which maybe I should describe briefly. So
yeah.
It's like, imagine we have two players, and they can choose between raising their own utility by 1 or raising the other player's utility by 3. And they only care about their own utility. Like they play against a stranger. For some reason, they don't care about the stranger's utility. And so they both face this choice. The sort of the traditional kind of like game theoretic analysis of this game by itself is that you should just raise your own utility by $1, and then both players will do this, and they'll both go home with $1 or 1 utilon or whatever. And of course, there's sort of some sort of tragedy, right? It would be nice if they could somehow agree to in this particular game to both give the other player $3 and to both walk home with the $3.
Yeah. And to sort of drive home what's going on, right? Like, if you and I are playing this game, right, the core issue is sort of no matter what you do, I'm better off giving myself the 1 utility or the $1 rather than like giving you 3 utility, because I don't really care about your utility.
Yeah.
So I guess there are 2 ways to put this. Firstly, just like no matter what you play, I would rather choose the like give myself utility option, commonly called defect, rather than cooperate.
Yeah.
Another way to say this issue is like in the version where we both give each other the $3, I'm better off deviating from that.
Yeah.
But if we're both in the like, only give ourselves $1, situation, neither of us is made better off by deviating. And in fact, we're both made worse off. So like, it's a sticky situation.
Yeah, that's all correct, of course. Okay, and now this program game setup imagines that we take some game, and now instead of playing it into this sort of direct way where we directly choose between cooperate and defect, like raise my utility by $1 or the other players by $3. Like instead of choosing this directly, we get to choose computer programs, and then the computer programs will choose for us. And importantly, so far this wouldn't really make much of a difference yet. Like, okay, we choose between a computer program that defects or a computer program that cooperates, or the computer programs that runs in circles 10 times and then cooperates or defects. Doesn't really matter.
Yeah.
But the crucial addition is that the programs get access to each other's source code at runtime. So I submit my computer program, you submit your computer program, and then my computer program gets as input the code of your computer program, and kind of based on that, it can decide whether to cooperate or defect, or you can take any other game. So it can like look at your computer program and sort of like, does it look cooperative, and depending on that, cooperate or defect. Yeah. Or it can look, is the 5th character in your computer program an A, and then cooperate if it is, and otherwise defect. No reason to submit this type of program, but this is the kind of thing that they would be allowed to do.
Yeah. Well, there are sometimes so this sort of like very syntactic analysis. A while ago, I was part of this like basically a tournament that did this kind of like prisoner's dilemma thing, like with these open source programs. And one strategy that a lot of people used was like, if I see like a lot of characters, like if I see a string where that string alone means like I will cooperate with you, then cooperate with that person, otherwise defect against that person. Which, like, I think if you think about it hard, this like doesn't actually quite make sense. But like, I don't know. There are sort of very syntactic things that in fact like seem kind of valuable, especially if you're like, if you're not able to do that much computation on the other person's computer program. Like, just simple syntactic hacks can like be better than nothing, I think.
Yeah, was this Alex Menon's tournament on Less Wrong, or was this a different
No,
tournament?
this is the manifold one.
Okay.
Yeah,
Okay.
so this is you had to write a JavaScript program. It had to be fewer than however many characters, and there was also a market on which program could win, and you could submit up to 3 things. So actually, I don't know, it's kind of annoyingly to me, like one thing I only realized afterwards is the thing you really should have done is like write 2 programs that cooperated with your program and defected against everyone else's.
Yeah.
And then like, or just cooperated with the program you thought was like most likely to win, and then you bet on that program.
Right.
Or even you could submit 3 programs, have them all cooperate with a thing that like you hoped would win and defect against everyone else, and then like bet on anyway. But in that setting, especially where you so in that setting there was like a timeout provision where like if the code ran for too long, like your bot would be disqualified, and also you had to write a really short program. So it was, I don't know. Some people actually managed to like write pretty smart programs, but if you weren't able to do that, I think like relatively simple syntactic analysis was like better than nothing, I think.
Yeah, I think there was this earlier tournament in like 2014 or something like that when there was less known about this kind of setting. And a bunch of programs there were also like based on these like simple syntactic things. But it's like in part because kind of like everyone was mostly thinking about these simple syntactic things.
Right.
Like it was all like a little bit kind of nonsense. Like I don't know, you would check whether the opponent program has like a particular word in it or something like that, and then I think the winning program had particular words in it, but it would just still defect. So it's like this sort of in some sense all of those dynamics are like a little bit sort of nonsense, or like they're not really tracking in some sense the strategic nature of the situation.
Fair enough. So going back, you were saying, you have your opponent's program and you can like see if the 5th character is an A, and then
what should one perhaps do? So I think this setting was first proposed in like I think 1984, something like that, and then kind of rediscovered or reinvented, I think, like 3 times or something like that, in various papers. And all of these initial papers find the following kind of very simple program for this prisoner's dilemma type situation, which just goes as follows: if the opponent program is equal to myself, like to this program, then cooperate, and otherwise defect. So this program is a Nash equilibrium against itself, and it cooperates against itself. So if both players submit this program, neither is incentivized to deviate from playing this program, right? Like if you play this program that checks that the 2 programs are the same, and if they are, cooperate, otherwise defect, you submit this program. The best thing I can do is also submit this program. If I submit anything else, you're going to defect. So I'm going to get at most 1 if I also defect, right? Whereas I get 3 if I also cooperate. So all of these original papers proposing the setting, they all find this program, which allows stable cooperation in this setting.
Right. And I think that like, so my impression, and maybe this is totally wrong, is I think for a while there's been some sense that like if you're like rational and you're playing the prisoner's dilemma against yourself, you should be able to cooperate with yourself. Like I think wasn't there some guy writing in Scientific American about like super rationality, and he held a contest like basically on this premise?
Hofstadter, I think.
Right.
I think also in the 80s or something. there's I've done a lot of work on this kind of reasoning as well, that like, I don't know, if you're like, I mean, for humans it's like a little bit hard to think about, right? If you like, you don't often face very similar opponents, or like it's a little bit unclear like how similar other people are. Like, I don't know, is your brother or whatever like someone who's related to you and like was brought up in a similar way? Are they like, very similar? It's kind of hard to tell. But for computer programs, it's very easy to imagine, of course, that you have two copies of GPT-4 or something like that and play a game against each other. It's a very normal occurrence in some sense. I mean, maybe not them like acting in the real world at this point, but this sort of having multiple copies of a computer program is quite normal. And there's sort of this related but to some extent independent literature on these sorts of ideas that that you should cooperate against copies.
Yeah,
basically.
But yeah, basically, I'm wondering if if this idea of like, cooperate against copies is like what inspired these like very simple programs.
Yeah, that is a good question. I don't know. I basically don't know to what extent this is the case. I know that some of the later papers on program equilibrium, I remember some of these like specifically citing this superrationality concept. But I think, I don't remember whether these papers by I think McAfee is like one of these who wrote about this in the 80s. I don't know whether they discuss superrationality.
Yeah, and it's kind of tricky because in that like, if you actually look at the computer programs, they're not doing expected utility maximization, right? They're just like, or they're not computing expected utility maximization. They're just like, if identical to me, cooperate, else defect, just like hard-coded in. And anyway, this is sort of maybe this is a distraction, but indeed these were like the first programs like considered in the program equilibrium literature. Yeah. So they sound great, right?
Yeah. So, I mean, they're great in that in the Prison's Dilemma, you can get an equilibrium in which you can get cooperation, which otherwise you can't, or like you can't achieve with like, I don't know, various naive other programs that you might write. But I think sort of in practice, and like it's kind of hard to, it's not so obvious what the practice of this scheme looks like. But like if you think of any kind of practical application of this, it's sort of a problem that the settings are somewhat complex, and now two people write programs independently, and then these programs, they sort of need to be the same somehow, or they need to, I mean, they're like slightly more general versions of these where they check some other syntactic properties. But basically, you require that you kind of coordinate in some way on like a particular kind of source code to write, which maybe in some cases you can do, right? Sometimes maybe we can just talk beforehand, like if we play this Prisoner's Dilemma, we can just explicitly say, okay, here's the program that I want to submit. Please submit the same program, and then you can say like, okay, let's go. But maybe in cases where we really write these programs independently, maybe at different points in time, and these programs, especially if they do more complicated things than play this Prisoner's Dilemma, it's very difficult to coordinate without kind of explicitly talking to each other on writing programs that will cooperate against each other. Because like even in the Prisoner's Dilemma, you might imagine that like, I don't know, I might have like an extra space somewhere, or maybe you write the program like if the two programs are equal, cooperate, otherwise defect, and I write like if the two programs are different, defect, else cooperate, and like all these like very minor changes would already break these schemes.
So okay, I think my first there's a lot to just ask about there. I think my first question is like, we have this notion of program equilibrium, like, what are we actually like? Are we trying to find Nash equilibria of programs? Are we trying to find like evolutionarily stable strategies? Like what are or maybe there are tons of solution concepts and we just want to play around with the space. But like, what are the actual like? What's the thing here?
Yeah. So the most like the solution concept that people talk about most is just Nash equilibrium. So that's like if you look at any of these papers and you look at the results, they'll prove like I don't know, these kinds of programs form a Nash equilibrium of the program game.
Yep.
Or, I mean, that is like the term program equilibrium literally just means Nash equilibrium of the game in which the players submit these programs.
Yep.
That is almost always the solution, the kind of game theoretic solution concept that people use. Then, I mean, usually a bunch of other things are sort of like a little bit more kind of implicit. Like it's gonna kind of clear that people are interested in finding sort of good Nash equilibria, right? Like in some sense, the whole point of the setup is, we start out with the prisoner's dilemma and sad. Everyone's going to defect against everyone else, and we're not getting to cooperation. And now we come in with this new idea of submitting programs that get access to each other's source code, and with this we get these cooperative equilibria. So that is usually, at least, I mean, it's often quite explicit in the text.
Yep.
That you're asking, can we find like good equilibria in some sense, like ones that are like Pareto optimal in the space of possible outcomes of the game or something like that.
Yep.
Yeah, and then additionally, a lot of the work after these early papers that do the syntactic comparison based program equilibrium are about this kind of intuitive notion of robustness, that you want to have equilibria that aren't sensitive to where the other program puts the spaces and the semicolons and like these syntactic details. But it's it is kind of interesting that this isn't formalized usually. And I also so the second paper that we talked about, we presented this at AAAI, and one game theorist came to our poster and said I don't know, to him it was sort of strange that there's sort of no formalization, or in terms of solution concepts in particular of this kind of robustness notion that I guess we'll talk about the programs that we're claiming, or that we're arguing are more robust, but this syntactic comparison based program, there's sort of some intuitive sense, and we can give concrete arguments, but it's sort of not formalized in the solution concept. There's no one of my favorites is called robust program equilibrium, but robust program equilibrium is not actually a solution concept in the sense that Nash equilibrium is, or trembling hand equilibrium is. The robustness is more some sort of intuitive notion that I think a lot of people find compelling, but in some sense it's not formalized.
Yeah, and it's funny because so I think it's very related. Okay, I see this as roughly within both the cooperative AI traditions and the Agent Foundations traditions, and I think these traditions are sort of related to each other. And in particular in this setting, in decision theory, I think there's also some notion of fairness of a decision situation. So sometimes people talk about suppose you have a concrete instantiation of a decision theory, meaning a way somebody thinks about making decisions. There are always ways of making that concrete instantiation look bad by saying suppose you have Caspar decision theory. We'll call it CDT for short. And then you can be in a decision situation, right? Where some really smart person figures out what decision theory you're running, punches you if you're running CDT, and then gives you $1 million if you're not. And there's a sense that this is unfair, but also it's not totally obvious. In that setting as well, I think there's just no notion of what the fair thing is, which is kind of rough because you'd like to be able to say, yeah, my decision theory does really well in all the fair scenarios. And it seems like it would be nice if someone figured out a relevant notion here. Are people trying to do that? Are you trying to do that?
Yeah, so I think there is some thinking in both cases, and I think the kind of notion that people talk about most is probably similar in both. So in this decision theory case, I think the thing that probably most people agree is that it should somehow, this decision situation should somehow be a function of your behavior. It shouldn't kind of check, do you run CDT, and if you do, get punched in the face. It should be sort of if in this situation you choose this, then you get some low reward, but sort of sort of this behavior should somehow be behavior based.
Yeah.
Which I think still isn't enough, but it's I mean, this sort of goes into the weeds of this of this literature. Maybe we can link some paper in the show notes.
Yeah.
But the condition that we give in the second paper, we I don't know, or maybe even in both of the papers that we're going to discuss, there's some explicit discussion of this notion of behaviorism, which also says you want, in the program equilibrium setting, it's sort of nice to have a kind of program that only depends on the other program's behavior rather than the syntax. And all of these approaches to robustness, trying to do some proofs about the opponent programs, about what the opponent program does, you try to prove whether the opponent will cooperate or something like that. All of these, to some extent, these notions that people kind of intuitively find more robust, they're all kind of more behaviorist, at least, than this syntactic comparison based idea.
Yeah, although it's tricky because I'm sorry, I don't know if this is going to the weeds that you want to postpone, but so this behaviorism based thing, if you think about the if you're equal to me, cooperate, else defect program, this is behaviorally different from the if you're unequal to me, defect, else cooperate program.
Yeah.
Right? It does different things in different situations. And therefore,
yeah.
Once you can define an impartial thing, right, then maybe you can say, well, if you act identically on impartial programs, then you count as impartial. But actually, maybe that's just a recursive definition, and we only need one simple program as a base case.
I think we do actually have. I think we have a recursive definition of simulationist programs.
Right.
That I think is a little bit sort of trying to address some of these issues. But yeah, it does sort of go into the weeds of how exactly, what exactly should this definition be?
Okay. Let's go back a little bit to Desiderata of program equilibria. So they're computer programs, right? So presumably, and this is addressed a bit in the second paper, but just runtime, computational efficiency, that seems like a relevant desideratum.
Yes, I agree.
And then I think that I imagine various desiderata to include, have a broad range of programs that you can work well with. And it seems like there might be some notion of just don't fail, if you fail not so badly rather than fail really badly.
Yeah.
I don't know if there's so this is slightly different from the notion of robustness in your paper, and I don't know if there's a good formalism for this. I don't know. Do you have thoughts here?
Yeah, I mean, in some intuitive sense, kind of what one wants, right, is that if I kind of slightly change my program, maybe even in a way that is sort of substantial, it's sort of, in the prisoner's dilemma, it's a little bit unclear, if I defect slightly more, if I don't cooperate 100%, but I cooperate 95%, it's sort of unclear, do you want to, to what extent should you be robust, right? Should you defect against me all of the time? But in other games where maybe there are different kinds of cooperation or something like that, you want, if I kind of cooperate in slightly the wrong way, the outcome should still be good. I think the main sort of I think in some sense, there's something here that's I think is conceptually quite clear, right? This sort of if you deviate in some kind of reasonable, harmless way, it should still be fine. We shouldn't defect against each other. We should still get a decent utility. But it's sort of the details are less clear. What exactly are the deviations? And it probably depends a lot on the game. And then there are a lot of these sort of things that in game theory are just kind of unclear. If I defect 5% more, how much should you punish me for that, right? And so I think that's why, a lot of these things aren't really formalized in these papers.
Okay. So now that we know what program equilibrium is, why does it matter?
Yeah, so there are lots of different possible answers to this question. I think the most straightforward one is that we can view program games like Program Equilibrium as sort of a model of how games could be played when different parties design and deploy AI systems. So this this whole thing of like having a source code that the other party can like look at and can maybe run, or can like look at the character 5 and stuff like that. This is sort of something that is like, it's like somewhat specific to computer programs. Like we can talk about like whether they're like human analogs still, but like when when we play a game against each other, it's sort of hard to imagine like an equivalent of this. Like I don't know. I have some vague model of how your brain works or something like that, but I don't really like. There's no source code. I can't really run you in some ways. Whereas for if we both write computer programs, this can just literally happen, right? Like we can just literally say, this is the source code that I'm deploying. I don't know. I have my charity or something like that, and I'm using some AI system to manage like how much to donate to different charities. I can't just say, look, this is the source code that I'm using for managing what this charity does. And here I think Program Equilibrium is or like program games are like quite a kind of literal direct model of how these interactions could go. Of course, they could also, like, you can also deploy the AI system and say like, well, we're not saying anything about how this works, in which case obviously you don't get these Program Equilibrium type dynamics. But it's a way that that they could go, and that people might want to use because it allows for cooperation. So it's sort of, I think the most direct interpretation is that it models like a kind of way that games could be played in the future when more decisions are sort of made by delegating to AI systems, and sort of as people in this kind of community who like think and to some extent worry about a future where lots of decisions are made by AI. This is like an important thing to think about, and meanwhile, because like to most like game theorists, this is sort of like a weird setting, because humans can't read each other's source code, right? And so it's sort of understudied by our lights, I guess. Because it's currently not a super important way that games are played.
Which is interesting because like so I guess we don't often have like games played with source code, with like mutual source code transparency, but there really are like computer programs that play economic games against each other in economically valuable settings, right? Like a lot of trading in the stock market is done by computer programs. A lot of like bidding for advertisement space is done by computer programs. So and like algorithmic mechanism design, so like mechanism design being sort of inverse game theory of like, if you want some sort of outcome, how could you figure out the game to make that happen? Like so algorithmic mechanism design being like that, but everyone's a computer. Like that seems like there's decent uptake of this as far as algorithmic game theory, there's decent uptake of that. So I'm kind of surprised that like the mutual transparency setting is not like more of interest to the broader community.
Yeah, I think I agree. I mean a lot of these settings. Okay, so I think the trading case, I guess, it's a case where decisions are made on both sides by algorithms. But usually because it's like, I don't know, it's a kind of a zero-sum game, right? You don't want to reveal to your competitors how your trading bot works. For there's a lot of this like mechanism design where you have an algorithm. I guess those are usually cases where it's sort of like unilateral transparency, right? Like I as a like I don't know, I auction off something and I'm saying, okay, I'm using this algorithm to determine who gets, I don't know, this broadband frequency or like whatever, like these things that are being auctioned off, right? So I guess those are cases with sort of unilateral transparency, and that is, I guess, studied much more in part because it's less like this also has been studied like kind of traditionally in game theory much more, like in some sense, like I don't know, you can view it as some sort of Stackelberg equilibrium, like you can view all mechanism design as like being a bit like kind of finding Stackelberg equilibria. And I guess Stackelberg even, I think like Stackelberg's analyses of game theory, like they even precede like Nash equilibrium. So
interesting.
So that is very old.
Yeah, where Stackelberg equilibrium is like one person does a thing and then the next person does a thing. And so like the next person is optimizing given what the first person does, and the first person has to optimize what's really good for me, given that when I do something, the other person will optimize what's good for them based on what I do.
Yeah.
So people look at Stackelberg equilibria in these sorts of games, and it's like a common thing. And it's an interesting point that you can sort of think of it as like one-way transparency.
I think one thing one could think about is like sort of like how much humans are in these mutual transparency settings. So yeah, I mean, I guess I already kind of said like for like individual humans, like if the two of us play a Prisoner's Dilemma, yeah, I have some model of you. I can't really read yourself. I don't know, like seems sort of speculative.
Yeah.
But there's this paper which I really like by Andrew Critch, Michael Dennis, and Stuart Russell, all from CHI, where of course you graduated from. And this is about program equilibrium as well. And the sort of the motivating setting that they use is institution design.
Yeah.
And the idea there is that, okay, institutions, you can view them as sort of like rational players or something like that, or like they make decisions and they play games with each other, right? Like the US government plays game with the German government or whatever. But institutions have some amount of transparency, right? They have laws that they need to follow. They have like constitutions. They also, because they're sort of composed of lots of individuals that in principle like one could ask, right? Like the German government could check all the social media profiles of all the people working for the US government and sort of learn something about how these people interact with each other or something like that. So there's some like very kind of concrete transparency there. And in particular, like, some things are really just sort of algorithmic type commitments, right? Like, I don't know, we don't negotiate with terrorists or something like that. It's sort of like a specific something that's like in the source code of a country in some sense, and it's kind of saying, specifying how it's going to choose in particular interactions. So I think that is a case where interactions between human organizations has this sort of transparency. And I guess I think that's like some evidence that we could get similar things with AI. At the same time, it's also kind of interesting that this hasn't motivated people to study this program equilibrium style setting, which I think is probably because, like, I think as a computer scientist, it's sort of natural to think like, the Constitution is basically just an algorithm, right? Yeah. It's also a little bit this sort of I don't know, like computer science people like explain the world to everyone else by using computer programs for everyone, and like the mind is a program and the Constitution is just a program, and we got it covered with our computer science stuff, which maybe some people also don't like so much. But I think it's at least I think it's a helpful metaphor still.
Fair enough. Okay, so some people do study program equilibria, and so just to set up the setting for your papers, before the appearance to the world of robust program equilibrium, what did we know about program equilibria beyond these simple programs that cooperate if your source code is mine?
Yeah, so we have some characterizations of the kind of equilibria in general that are allowed by these syntactic comparison-based programs. Not sure how much to go into that at this point, but yeah, maybe we'll get into this later.
I mean, my understanding is it's just like I think I can do this quickly. My understanding is basically like if any equilibrium that's better off for all the players than like unilaterally doing what they want, you can get with program equilibrium, because you can just be like, or maybe it's like you have to have punishments as well, but something roughly like this, right? You can have programs being like, you have to play this equilibrium. If you don't, then I'll punish you, and like just write up a computer program saying like, if you do this, if you're equal to me, then if you're equal to me and therefore play this equilibrium, then I'll play this equilibrium. If you're not, then I'll do the punish action.
Yes. That's basically right.
Okay. Is it only basically right?
I mean, it's so no. I think it's basically right.
Okay.
Like I think it's fully right. I mean, it's sort
Okay,
of like
cool.
in the way it's sorry. The basically it's just like in the way that all kind of natural language descriptions. Yeah. It is these. Yeah. You can get anything sort of that is better for everyone than what they can get if everyone punishes them, right?
Yeah.
Which might be quite bad, right? Like, so for example, in the prisoner's dilemma, we had this nice story of how you can get mutual cooperation, but you can also get, I don't know, one player cooperates 60% of the time, the other player cooperates 100% of the time. And the reason why the 100% of the time cooperator doesn't cooperate less is that the 60% cooperator kind of says like, well, yeah, if we're not both submitting the program that plays this equilibrium, I'm going to just always defect, right? So like in the prisoner's dilemma, you can get anything that is at least as good as mutual defection for both players. So you, in some sense, like kind of like almost everything can happen. I mean, it can't happen that like one player cooperates all the time, the other player defects all the time, right? Because then the cooperator would always want to defect. But yeah, I mean that's sort of the basic picture of what's going on here. So this is so that has been known, and then post Tenenholz, which is like one of these papers, like I think the paper that termed the coin program equilibrium and gave this syntactic comparison based program and this folk theorem, as it's called, of what kind of things can happen in equilibrium. After that, most papers have focused on this sort of how do we make this more robust idea, and in particular what existed prior to the robust program equilibrium paper are these papers on making things more robust by having the programs try to prove things about each other.
Yep.
So here's maybe the simplest example of this that like one doesn't need to like know crazy logic for.
Yep.
So you could write a program, like in the prisoner's dilemma, you could write a program that tries to search for proofs of the claim, if this program cooperates, the other program will also cooperate.
Okay.
So your program is now very large, right? It has this like proof search system. It can find proofs about programs.
Yeah.
But basically, you can still describe it like relatively simply as I try to find a proof that if I cooperate, the opponent cooperates, and then I cooperate, otherwise it defect. And it's sort of like, it's not that difficult to see that like this kind of program can cooperate against itself, right? Because if it faces itself, it's relatively easy to prove that it will, that if I cooperate, the opponent will cooperate, right? Because the statement is just it's an implication where like both sides of the implication arrow say exactly the same thing.
Yeah.
And at the same time, this is more robust because it's like this will be robust to changing the changing the spaces and so on, right? Like it's relatively easy to prove, if this program outputs cooperate, then this other program, which is the same except that it has the spaces in different places or like switches things around in some way that doesn't really matter. That this will also output that thing. That will also output cooperate. So this is a basic kind of proof-based approach that will work. This was, so I think the first paper on this is by Barras et al. I think there are like two versions of this which have different first authors, which is a little bit confusing. I think one of it is on one of them Barras is the first author, and on the other one it's La Victoire, I think, or like I think it's an American. So probably a less French pronunciation is correct. But
I actually think he does say La Victoire.
Oh, okay.
I think. I'm not 100% certain.
Okay.
Write in, Patrick, and tell us.
So those papers first proposed these proof-based approaches. They actually do something that's more clever and where it's much harder to see why it might work.
Yeah.
So I described a version where the thing that you try to prove is if I cooperate, the opponent will cooperate.
Yeah.
They instead just have programs that try to prove that the opponent will cooperate. So you just do, if I can prove that my opponent cooperates, I cooperate, else I defect. And this is like much less intuitive that this works, right? You would intuitively, you would think like, surely this is like some weird infinite loop, right? If this faces itself, like if I can, like, you know, I'm gonna think like, what does the opponent do? And then, well, to think about what my opponent will do, to prove anything about them, well, I need to okay, they'll try to prove something about me, right? And you run into this infinite circle. Like you would think that this like basically the same as the sort of one very naive program that you might write is just like run the opponent program. If it cooperates, cooperate, otherwise defect, right? And this really does just run in circles.
Yeah.
And you would think that just doing like proofs instead of this running the opponent program, that this you have the same issue. It turns out that this does that this you can find these proofs, which follows from a sort of like somewhat obscure result in logic called Loeb's theorem, which is it's a little bit related to Gödel's second incompleteness theorem. Yeah, I think probably. Like it's, I don't know, with Loeb's theorem, it's like relatively easy to prove, but kind of like hard to like I don't know, it's like a very like you kind of need to just write it down proof, and then it's sort of relatively simple, but it's hard to, I don't know, it's hard to give an intuition for it, I think.
I think it's also one of these things that's like hard to state unless you're like careful and remember. So I've tried to write it down. It's like, if you can prove that a proposition would be true, okay. Take a proposition P.
Mm-hmm.
Loeb's theorem says that if you can prove that, if you could prove P, then P would be true. Then you would be able to prove P.
Mm-hmm.
So if you can prove that the provability of a statement implies its truth, then you could prove the thing. And the reason that this is like sort of non-trivial or something is it turns out that you can't always prove that if you could prove a thing, it would be true, because you can't prove that your proving system works all the time, and you can construct funky self-referential things that work out. So unless I have messed up, that is Loeb's theorem.
Yes.
And so my recollection is the way it works in this program is like, so basically you're checking if the other program would cooperate. Like imagine we're both these defect unless proof of cooperation programs, right? Like I'm like, okay, well, I want to check if you would cooperate given me. If you would cooperate given me is the same as if I would cooperate given you. So okay, so it's here's the thing that I definitely can prove. If you can prove that, if I can prove that I cooperate, then you cooperate, right? But crucially, the I and the you are actually just the same because we're the same program. So if it's provable, then we cooperate, then we cooperate. Loeb's theorem tells us that we can therefore conclude that it is provable that we cooperate.
Yes.
Therefore, we in fact cooperate. And my understanding is like, so what do we actually do? I think we prove Loeb's theorem and then apply it to our own situation, and then we both prove that we both cooperate, and then we cooperate. I think that's my recollection of how it's supposed to go.
At least that would be one way.
Yeah. I suppose there might be even shorter proofs.
Yeah. But yeah, that is basically correct. Good recollection of the papers.
Yeah. Well, there were a few years in Berkeley where like every couple weeks somebody would explain Loeb's theorem to you and like talk about Loebian cooperation, and it was so eventually you remembered it.
Okay, nice. Yeah. Yeah, it's a very nice. I think it's a very nice idea. I actually don't know how they made this connection. I mean, also Loeb's theorem is relatively obscure. I think in part because it's sort of like it doesn't prove that much more than Gödel's second incompleteness theorem, right? Like it's a kind of a result like if you can, like, so Gödel's incompleteness theorem is like you can't, like a logical system can't prove its own consistency. Like here it's sort of the same thing, right? Like you can't prove like if I can prove something it's true without just being able to prove the thing. And so and I think that's probably one reason why Loeb's theorem isn't very widely known. And sort of like for this, it's sort of like, I feel like it's sort of a result that like for this thing, it's like happens to be like kind of exactly the thing you need, right? Like once you have it written down, it's this cooperation property like follows almost immediately. But
how they made the connection.
But yeah, how did they?
I think I know this. Or I have a theory about this. So originally, so before they were talking about Loebian cooperation, there was this Loebian obstacle or Loebsticle, as they said, to self-trust, right? Where like they were like, the problem, like you might want to say like, I'm gonna like create a successor program to me, and like if I can prove that the successor program is going to do well, then or like I don't know, all the programs are going to be like, if I can prove a thing is good, then I'll do it. And can I prove that like a program that I write is going to be able to do stuff? And it's a little bit rough because if I can prove that you could prove that a thing is good, then I could probably prove that the thing was good myself. And so why am I writing the... So maybe this just caused Loeb's theorem to be like on the mind of everyone. I don't know. I have this theory, but I don't think I've heard it confirmed by any of the authors.
Okay, that's a good theory, I think.
Okay. So we had this Loebian cooperation idea floating around. And this is like one thing that was known before these papers we're about to discuss. Is there anything else that important?
So there is, I think there's like, there is a little bit more kind of like extension of this Loebian idea. So I think there's like one weird thing here, right, is that we have these programs like if I can prove this, then I cooperate. Of course, whether I can prove something is not decidable, right? There's not like an algorithm that like tries for 10 hours and then it gives up and like, right? Like that's not what I can provability would normally mean. And so there's a paper by Andrew Critch from I think 2019 that shows that actually this like Loeb's theorem still works if you consider these sort of like bounded, like you try for like with like a given amount of effort, like specifically like you try like all proofs of a given length, I think is the constraint, and it sort of shows that some version of Loeb's theorem still holds, and it's still enough to get this Loebian cooperation if the two players kind of like consider proofs up to like a kind of long enough length. They can still,
and it doesn't have to be the same length.
It doesn't have to be the same length. Importantly,
it just has to be the length of that paper.
Right.
Which is great, right? Very fun result. So there's Loebian cooperation. There's parametric bounded Loebian cooperation. Anything else of note?
I think there's not. I think one other thing that I think is kind of interesting. I mean, this is not really like a important fact, but I think it's like an important thing to understand, is that the for the Loebian bots, it's sort of like it matters that you check that you try to find a proof that the other player cooperates rather than trying to find a proof that the other player defects, and the same is true. The same is true for the defect case, I guess. So this like implication case that I described, like if you try to check like is there proof that if I defect the opponent will defect, I mean not sure why you would do that. But
you might do it based on like, or I mean you can imagine similar things of just like, okay, if I try and punish you, will you? Or if I defect, will you cooperate with me naively, like a sucker? If so, then I'm just definitely going to defect, right?
Right. Though then I guess you would not, check for some other property.
Or you would check, like, if I defect, will you defect? If so, then I'll cooperate. Like, maybe that would be the program.
Yeah, right? Maybe that is even the more sensible program. And I guess that, there I'm not sure whether this cooperates against itself. So in the... like in this there's this
Wait, it must cooperate, right? Because like suppose.
Okay, let's think.
So suppose we're the same program, right? Then it's basically like if provable defect, if and only if provable defect, then cooperate, else defect. But provable defect, if and only if provable defect. It's the same. Like you don't have to go into the like you can just see that it's the same expression on both sides.
Right, I agree.
So you must
this will cooperate.
Yeah.
Yeah. This is not an equilibrium though, right? Like if the opponent just submits defect bot, you're gonna cooperate against it, right?
Yes. It's not an equal. It is a program.
It's
not an equilibrium.
Yeah.
Okay.
Okay. I assume
I got us off track, I fear.
Wait,
yeah, but you were saying that you have to like you kind of want to be proving the good case, not the bad case.
Yeah. So I guess for maybe let's do the version from the paper. Like if I can prove that you cooperate, I cooperate. Otherwise, I defect.
Yeah.
Right. Like if you think about it, like in this program, it doesn't really matter that like mutual cooperation is sort of the good thing,
yeah,
and mutual defection is the bad thing. Like ultimately, it's just we have two labels, cooperate and defect.
Yeah,
could call them A and B instead, and it's just like if I can prove that you output label A, I also output label A. Otherwise, I'll output label B, and sort of regardless of what these labels are, this will result in both outputting label A, and if label A happens to be defect rather than cooperate, these will defect against each other. Yep. So it sort of matters that you need to sort of like I don't know, try the good thing first or something like that.
Yeah. It's I guess like maybe the most intuitive way of thinking about it, which I haven't thought about it a ton, so this may not be accurate, but it feels like it's like, okay, you're setting up a self-fulfilling prophecy of like, or if the other person happens to be you, then you're setting up a self-fulfilling prophecy. And you want to set up the good self-fulfilling prophecy, not the bad self-fulfilling prophecy.
Yeah.
I think this is true in this setting. My impression is that there's also like decision theory situations where you want to like try and prove, where you really care about the order in which you try and prove things about the environment. And I forget if self-fulfilling prophecy is like the way to think about those situations as well, even though they're conceptually like related. We can perhaps leave that to the listeners if it's too hard to figure out right now. Okay, so now that we've known this like sad world that's confusing and chaotic, perhaps we can get the light of your papers.
Okay. I mean, I should say I really like the proof-based stuff. I mean, we can talk a little bit about what maybe the upsides and downsides are. I mean, it is confusing. I would think the main, I would think that one issue is with it is that sort of like in practice, you know, what programs can one really prove things about, right? It's a little bit.
Yeah, I mean, my intuition is that it's like the point of that work is supposed to be like, like it seems like it's supposed to be modeling like cases where you have like good beliefs about each other that may or may not be exactly proofs, and you hope that something like Loeb's theorem holds in this like more relaxed setting, which it may or may not. I don't exactly know, but
yeah, I agree. I also kind of view it this way, which is sort of like a more metaphorical way. There's some distance between the mathematical model and the actual way it would work then.
But I want to hear about your paper.
Right. Okay. So now let's get to my my paper. So my paper is on whether we can get these cooperative equilibria, not by trying to prove things about each other, but by just by simulating each other.
Yeah.
And I already mentioned that like there's this sort of super naive but kind of intuitive approach that you'd like to run the opponent against, like you'd like to do like run the opponent with myself as input, see if they cooperate. If they do cooperate, otherwise defect. Right? It's sort of this like very obvious like intuition, maybe like from like, I don't know, tit for tat in repeated games, that you wanna reward the other player for cooperating and get a good equilibrium that way. And the problem with this, of course, is that it doesn't hold, right? If both players do this.
Yep.
I guess this would work if you play this sequentially, right? Like, we talked about the Stackelberg stuff earlier, right? Like if I just submit a program first, and then you submit a program second, then it would work for me to submit a program that says, run your program, cooperate if it cooperates, defect if your program defects, and
Yeah.
then you would be incentivized to cooperate.
Yeah.
But if both players play simultaneously, infinite loop, so kind of doesn't work.
If we had reflective oracles, then it could work, depending on the reflective oracle. But that's a whole other bag of worms.
Yeah, I guess reflective oracles are, I mean, probably shouldn't get into it, but it's sort of like another model that's like a little bit, maybe it's also a little bit like, I don't know, maybe it's like a little bit sort of in between the proof-based stuff and the simulation stuff.
Yeah.
But
At any rate.
yeah, so it turns out there's like a very simple fix to this issue, which is that you can just, like, instead of just always running the opponent and cooperating if and only if they cooperate, you can avoid the infinite loop by just cooperating with epsilon probability, and only if that's sort of this like epsilon probability clause doesn't trigger, only then do you run the other program. So like your program is just like I don't know, flip a very, very biased coin, like epsilon is a small number, right? So you check whether like some low probability event happens. If it does, you just cooperate without even looking at the opponent program. And otherwise, you do simulate the other program and you copy whatever they do. So you cooperate if they cooperate, defect if they defect.
Yeah.
And the idea is that basically this just like it's sort of the same intuition as the, just copy, like just simulate the opponent and do this sort of instantaneous tit for tat.
Yeah.
Except that now you don't run into the infinite, this like running for infinitely long issue, because it might take a while, but like eventually you're gonna hit this these epsilon clauses, right? Like if we both submit this program, then okay, probably like there's some chance that I'm immediately cooperating, but most likely I'm gonna call your program, which might then also immediately cooperate. Most likely it's gonna call my program again, and so on. But at each point we have a probability epsilon of kind of like halting, and like with probability 1 will eventually halt.
Yeah. And this is a special case of this like general construction you have in the paper, right?
Yeah. So this is for the prisoner's dilemma in particular, right? Where you have these two actions that happen to be cooperate and defect.
Yeah.
In general, you can in general there are like two things that you can specify here, right? Like you specify what happens with the epsilon probability, and then the other thing that you specify is what happens if you simulate the other player, you get some action out of the simulation, and now you need to kind of react to this in some way. And so in like the paper draws this connection between these epsilon grounded PyBots, as they're called, and repeated games where you can only see the opponent's last move.
Yeah.
So it's kind of similar to that, where maybe like this like epsilon clause where you don't look at your opponent. It's kind of like playing the first round where you haven't seen anything of your opponent yet.
Yeah.
And I guess in the prisoner's dilemma, it's sort of like there's this well-known tit for tat strategy which says like you should cooperate in the beginning, and then at each point you should look at the opponent's last move and copy it. So cooperate if they cooperate. But in general, you could have these myopic like strategies for these repeated games where you do something in the beginning, and then at each point you look at the opponent's last move and you react to it in some way. Maybe, I don't know, do something that's equally cooperative, or maybe something that's like very slightly more cooperative to kind of like slowly get towards cooperative outcomes or something like that. So you could have these strategies for the for repeated games, and you can turn any of these strategies into programs for the program game.
So one thing that's that I just noticed about this space of strategies. So this is strategies that only look at your opponent's last action, right?
Yes.
So in particular, like so there's this other thing you can do, which is called like win, stay, lose, switch, where like if you cooperated against me, then I just do whatever I did last time. If you defected against me, then I do the opposite of what I did last time. And it seems like well, it seems like this is another reason that thing that your next paper is going to fix. But that in this strategy, it seems like I can't do this, right?
Yes. Yeah. It's really very restrictive. You can really. Ultimately, you can. I mean, most of the time, you're gonna see one action of the opponent. You have to react to that somehow, and that's it.
Yeah, but it's a cool. So it's this nice idea, and so it's basically this connection, right, between like if you can have a good iterated strategy, then you can write a good computer program to play this like mutually transparent program game, right?
Yeah.
How much do we know about good iterated strategies?
That is a good question. So I think for the program for the iterated prisoner's dilemma, there's sort of a lot about this. There's sort of there are a lot of these tournaments for the iterated prisoner's dilemma. I'm not sure how much there is for other games actually. You might I don't know I don't know iterated stack hunt or something like that. I guess maybe for a lot of the other ones it's sort of too easy or so. There's some literature, and I mean, you can check the paper. Like, there are like various kind of notions that people have looked at, like exploitability of various strategies, which is sort of like how much does the other player kind of like how much more utility can the other player get than me,
right?
If I play the strategies, like for example, tit for tat. If the opponent always defects, you're gonna get slightly lower utility than them because in the first round you cooperate and then they defect, and then in all subsequent rounds both players defect, and so it's like very slightly exploitable but not very much. So there are these notions that have been studied, and then in my paper I kind of like transfer these notions. Like you get if you take a strategy for the iterated prisoner's dilemma and for any repeated game, and it's like has like some amount of exploitability, well, the analogous similar ϵGroundedπBot strategy has like the same amount of exploitability. But I'm not sure. I think this is also kind of an interesting question in general. It's like sort of like how much like qualitatively different stuff is there even like in this purely ϵGroundedπBot space. Like if all you can do is look at the other, like one action of the opponent and react to this action, like how much more can you even do than things that are kind of like this sort of tit for tat? Like I mentioned this, like being like in more complex games, maybe you want to be like slightly more cooperative. So that's sort of the idea is that if you like, I don't know, you after like a bunch of simulations, you eventually become very cooperative or something like that.
Yeah. Okay, I have a theory. So okay, in my head, I'm thinking like, okay, what's the general version of this? Mm-hmm. And I can think of two ways that you can generalize, right? So here's what I'm imagining you should do in general. Okay, you have a game, right? First, you think about, okay, what's the good equilibrium of this game, right? And then what do I want to do if the other person doesn't play ball, right? It seems like there are two things I could do if the other person doesn't join me in the good equilibrium. Firstly, I could like do something to try and punish them, right? And secondly, I can do something that will like make me be okay, like be good enough no matter what they do, right? Like I'm not exactly like I don't exactly know how you formalize these, but my guess is that you can formalize something like these, and my guess is that these will look different, right? And so you can imagine saying like, okay, with epsilon probability, I do my part to be in the good equilibrium, and then the rest of the time I simulate what the other person does. If they play in the good equilibrium, I play in the good equilibrium. If they don't play in the good equilibrium, then depending on what I decided earlier, I'm either going to like punish them, or I'm going to do a thing that's fine for me. Or you can imagine that I like randomize between those. Like maybe there's some like best of both worlds thing with randomizing. I don't exactly know, but okay, do you have a take on that?
I mean, there's at least one other thing you can do, right? Which is try to push, like try to be like slightly more cooperative than them, in the hope that like you just kind of like,
right,
like by doing this repeatedly, like if you like imagine like the repeated game, right? At any given point, you might want you might want to be try to be a bit more cooperative in the hope that like the other person will figure this out, that this is what's going on, and that you're always going to be like a little bit more cooperative than them.
Yeah.
And that this will kind of lead you to the good equilibrium, or like to a better equilibrium than what you can get if you just punish. I mean, punish usually means you do something that you wouldn't really want to do. You just do it to incentivize the other player, or even the kind of like, okay, well, what you're gonna go and do whatever, but I'm just gonna do something that makes me okay.
I mean, is the like, so the be more cooperative than the other person thing? I feel like that's already part of the strategy. So like, okay, here's what the thing I could do with epsilon probability: do the like good equilibrium, then simulate what the opponent does. If they do the good thing, if they're in the good equilibrium, then I join the good equilibrium. If they don't join the good equilibrium, then with epsilon probability, I be part of the good equilibrium, and then otherwise I do my like other action. Like that with epsilon probability for being slightly more cooperative, like you could have just folded that into the initial like probability, right?
Right. I guess the difference is that you can like you can be sort of like you can be epsilon more cooperative in like a deterministic way, right? Like with this like epsilon probability thing.
Yeah.
Like you're like some of the time you play your favorite equilibrium, or like the equilibrium that you would like to play.
Yeah.
But this alternative proposal is that like you always become slightly more cooperative, right? Which is I mean, I'm not sure how these things play out. I would imagine that like for characterizing what the equilibria are, probably all you need is actually the punishment version, like the but I would imagine that if you want to play like some kind of robust strategy, you would sometimes do this like move into like a slightly more cooperative direction or something like that. I guess another thing to think about is that you could have all of these games where there are like lots of ways to cooperate, and they sort of like vary in how good, like in how like they distribute the gains from trade or something like that, right? And then there's sort of a question of what exactly happens if your opponent is like, I don't know, they play something that's kind of cooperative, but sort of like in a way that's like a little bit biased towards them. In which case, I guess maybe you would view this as just like a form of punishment if you then say like, well, I'm going to stay like somewhat cooperative, but I'm going to punish them enough to make this not worthwhile for them or something like that.
Yeah, if there's different cooperative actions that are more or less cooperative, then it definitely makes sense. Okay, but at the very least, I think there are at least two strategies in this space. Although maybe I don't know if both of them are equilibria, to be fair. I think so okay, there are a few things about this strategy that I'm like interested in talking about. So the first thing that seems kind of strange is, suppose like I'm this like we're both playing the same like kind of tit for tat but in our heads strategy, right?
Mm-hmm.
The time that it takes us to eventually output something is order 1 on epsilon, right? On average, because like with epsilon, each round with epsilon probability we finish, and then like it takes like 1 on epsilon rounds for that to happen, right?
I think that's roughly right. I think it's like a geometric series, right? Like, is it? I think it's like roughly 1 over epsilon.
Yeah, it's 1 minus epsilon over epsilon, which is very close to 1 on epsilon. Yeah. So like that strikes me as a little bit wasteful, right? In that like, so the cool thing about the Löbian version was like the time it took me to like figure out how to cooperate with myself was just the time it took to like do the proof of Loeb's theorem. No matter like how like it was sort of this constant thing, right? Whereas with like the epsilon version, like the smaller the epsilon is, the longer it seems to take for us, and we're just going like back and forth, right? We're going back and forth and back and forth and back and forth. I have this intuition that there's like something wasteful there, but I'm wondering if you like agree with that.
I think it's basically right. Like I think it basically is like I don't know. I think I share the intuition that it's sort of yeah, there's something like, yeah, especially if you have like a very low epsilon, right? There's a lot of just kind of like doing the same back and forth thing for a long time without, yeah, without getting anything out of it. I suppose, like, one thing is that, yeah, you could try to speed this up, right? Like if you like if so let's say I run your program, right? Then instead of like just running it in the naive way, I could do some analysis first. Like I can, it's sort of like in a way that like a compiler would, like if you have like a compiler of a computer program, it might be able to like do some optimizations. And so like maybe I could analyze your program, analyze my program, and I could tell like, okay, what's going to happen here is that we're gonna do a bunch of like nothing, like until this like epsilon thing triggers. So really, instead of like doing like this actually calling each other, we just need to like sample the kind of depth of simulations according to this geometric distribution, like the distribution that you get from this like halting at with probability epsilon at each step.
Yeah.
So you could do this analysis, right? Like if you expect, especially if you expect that your opponent will be an epsilon grounded fairbot, you might like explicitly sort of like put in your compiler or whatever something to like check whether the opponent is like this epsilon grounded fairbot, and if so, we don't need to do this like actually calling each other. We just need to sample the depth, and then you just need to, yeah, then like in some sense the computation that you need to do is like sample the depth, then sample from what the opponent, what whoever is at that, like whoever halts at that point, like sample from their like sort of base distribution, like their like blind distribution, and then sort of propagate this through all of the like the function that both players have for taking a sample of the opponent's strategy and generating a new action. And if this is all very simple, then you can show that like in principle, like your compiler could say, okay, I'm here doing all of this, like for the epsilon grounded fairbot in particular, like the epsilon grounded fairbot is the version for the prisoner's dilemma. You in principle, like your compiler could directly see, okay, what's going to happen here? Well, we're going to sample from this geometric distribution, then cooperate will be sampled, and then a bunch of identity functions will be applied to this. So this is just cooperate without needing to do any like any actual running this, like doing recursive calls by something with a stack and so on. Like you don't actually need any of this.
I do think there's something like very intuitively very compelling about like, okay, like if I can prove that like, you know, the good thing happens or whatever, then like do the proof based thing. If I can't prove anything, then do the simulation stuff. It seems intuitively compelling. I imagine you probably want to like do some checks if that works on the proof based side, depending on the strategy you want to implement.
I mean, the thing I'm proposing is not to have this like fallback, like the proof fallback, but just that you always do the epsilon grounded fairbot thing, for example, or the epsilon grounded pybot. You just like you're like instead of like calling the opponent program in a naive way where you actually run everything, you throw it in like this clever compiler that analyzes things in some way, and maybe this compiler can do like some specific optimizations, but it doesn't like, it's not a fully general like proof searcher or anything like that.
I mean, it's checking for some proofs, right?
Yeah, it's checking for some specific kinds of proofs. Which I guess is like, I mean, that's how like modern day compilers, I assume, work, right? Is that they like understand like a specific kinds of optimizations and they can make those. But they don't. I mean, they don't have a fully general proof searcher or anything like that.
I guess I was imagining a slightly like. Sorry, when you said that, I was half listening and then half thinking about a different thing.
Right.
Which is like, you know, you could imagine like epsilon grounded fairbot, which is, okay, first, if your source code is equal to mine, then cooperate. Else, if your source code is the version of epsilon grounded fairbot that doesn't first do the proof search, then cooperate. Else, with probability epsilon cooperate, probability 1 minus epsilon do what the other person does, right?
Yeah.
And that would like that probably, so that particular version probably doesn't actually get you that much because like the other person like added some spaces in their program, and then I'm like, but you could do some proof stuff instead of there. Yeah, I guess there are a few possibilities here.
Yeah.
But it does seem like something's possible.
Yeah. I mean, for what it's worth, in general, I think these different kinds of these different kinds of ways of achieving this more robust program equilibrium, they are compatible with each other. Like if I do the epsilon grounded pBot and you do the Löbian bot, they are going to cooperate with each other.
You're sure?
I'm pretty sure. Yeah.
Okay. You've probably thought about this.
Yeah. I read like a paper about like, I mean, it's not a real paper. It's sort of like a note.
Okay.
On this. Yeah. Because like if let's say you're the Löbian bot, so you try to prove.
Yeah.
Like maybe let's take like the simplest version, so we don't need to go down the Löb's theorem path again.
Yeah.
Let's take the simplest version, which is just can I prove that if I cooperate, you cooperate? You can, like, if you're the Löbian bot and I'm epsilon grounded pBot, epsilon grounded pBot, you can prove that if you cooperate, I will cooperate, right? Because, well, I'm epsilon times.
Sorry, can you say that without using you and I?
Okay, yeah. So am I allowed to say I submit a program that's...
Yes, you are.
Okay, so I submit a program that says that is just the epsilon grounded pBot.
Yes.
So just with epsilon probability cooperate, otherwise simulate you and do what you do.
Yep.
And your program is if it's provable that if this program cooperates, the other program cooperates, then cooperate, and otherwise defect.
Yep.
Okay, so like so let's think about your program.
The proof-based one.
The proof-based one.
Yeah.
So your program will try to prove if it cooperates. Caspar's, like my program, will the epsilon grounded pBot will cooperate.
Okay, so proof-based program is trying to prove if proof-based program cooperates, then sampling program cooperates, and it will be able to prove that. I think the other implication is slightly trickier, but maybe you only care about the first implication.
Yeah, sorry, what is the other implication?
That if the sampling-based program cooperates, then the proof-based one will cooperate. Actually, maybe that's not so bad because...
But do you actually need this? Like, you can prove that the proof-based program will succeed in proving this implication.
Yeah.
Right? And it will therefore cooperate.
And that's how it proves that it will do it in the other direction.
And, well, I mean, that's how one can then see that the epsilon grounded pBot will also cooperate.
Yeah.
Because it will, well, with epsilon probability, it cooperates anyway. And with the remaining probability, it does whatever the proof-based thing does, which we've already established is to cooperate.
Yeah.
Yeah, sorry, does this leave anything open, or?
So the thing I was curious about is... Oh, yeah, I think I was just thinking about a silly version of the program where the proof-based thing is checking can I prove that if I cooperate... So can I prove that if my opponent will cooperate, then I will cooperate? But I think you wouldn't actually write this because it doesn't make any sense.
Yeah, no, I think that seems harder, though. I don't know, maybe if we think about it for 2 minutes, we'll figure it out. But I think one wouldn't submit this program.
Yeah. I next want to ask a different question about this like tit-for-tat based bot. So this bot is going to cooperate against CooperateBot, right? The bot that always plays Cooperate. That seems pretty sad to me.
Yeah.
Right? I'm wondering, how sad do you think that this is?
Yeah, I'm not sure how sad. So, I have two answers to this. The first is that I think it's not so obvious how sad it is. And the second is that I think this is a relatively difficult problem to fix. So, on the, like, how sad is this? Okay, so I agree that, like, it's sort of, like, I don't know, it sort of depends a little bit on, like, what you expect your opponent to be, right? If you imagine, like, you run around the world and, you're this program, you've been written by Daniel, and you run around the world and you face opponents, and most of the opponents are just inanimate objects that weren't created by anyone for strategic purposes.
Yeah.
And now you face just like the classic like rock that says cooperate on it, and it happens to be a rock that says cooperate, right?
Yeah.
You should obviously you don't really want to cooperate against that, but like here's another possibility. So let's say you do like we play this program equilibrium game literally. And you submit your program, right? And you know that the opponent program is like written by me, by Caspar, who probably thought about some strategic stuff, right?
Yeah.
Then, okay, it could be that I just wrote a CooperateBot, right? And that you can now get away with defecting against it. But maybe you could also imagine that like maybe there's like something funny going on. And so, for example, one thing that could be going on is that I could like here's a completely or like a pretty similar scheme for achieving cooperation in the program equilibrium game, which is based on like not the programs themselves mixing, but the players mixing over what programs to submit. And so I might
mixing meaning randomizing.
Yeah, randomizing. Yeah. Very good. So I might randomize between the program that just cooperates, so CooperateBot, the program that cooperates if and only if the opponent cooperates against CooperateBot. So it's sort of like a second order CooperateBot or like something like that.
Yeah.
And then you can kind of imagine how this goes on, right? Like at each of my programs is sort of some hierarchy of programs that check that you cooperated against the one lower the list. And like in some sense, this is kind of similar to the epsilon grounded fairbot. I guess in that like at each stage you like kind of like you can look at my program and like okay, it would be like maybe I could just defect or something like that, but the problem is you might be in a simulation of the programs that are like higher in the list. And so here you would want, if I submit this distribution, you would still want to cooperate against my CooperateBot. Of course. So that is one reason to want to cooperate against CooperateBot.
Yeah, I guess it's tricky because like it suddenly means that it really matters how like which things in my environment I'm modeling as like agents and which things in my environment that I'm modeling as like non-agents, right? Because like so in my actual environment, there are like I think there are many more non-agents than there are agents. Yeah. And then, like, not only do I have to... So take this water bottle, right? Like, not only do I have to, like, model it as a non-agent, but I've also... It seems like maybe I've also got to be modeling, like, well, what are the other things it could have done if physics were different, right? Okay. And then, like, it feels like I'm going to... Like, it seems like if I have this sort of attitude towards the world, a bunch of, like, bad things are going to happen, right? And also, like, if I'm in a strategic setting with, like, you know, other agents that are trying to be strategic, like, I think it does actually... I think you do actually want to be able to say things like, hey, if I defected, would you cooperate anyway? In that case, I'll just defect. But if your cooperation is dependent on my cooperation, then I'm going to cooperate. Which is hard. It's hard to do with this construction because I'm checking two things, and that, like, explodes into a big tree. But, like, I think this seems to me like something that you do want to do in the program equilibrium world. So yeah, I guess those are two things. I'm wondering, like, what your takes are.
Yeah, so I mean, I agree that it would be nice to know how to do the, like, this sort of, like, could I, like, for this given opponent program, could my defecting, like, would it make the opponent defect? And so, like, this, like, I think, like, a program that exploits CooperateBot and cooperates against itself in some robust way, I agree that this would be desirable. I guess we can say more about, like, to what extent this is feasible. I do think that basically, like, in some sense, one does just have to do the, you know, form the beliefs about, like, what the water bottle could have been and things like that. Like, I guess with the water bottle, I don't know, like, I mean, it's sort of like a weird example, but, like, with the water bottle, I guess you would have to think about, like, is it is there someone who has like a reason, like do you have a reason to believe that there's someone who's like simulating what you do against the water bottle, and like depending on that does something, right?
Right.
And like I guess in the strategic setting where like that the opponent program is submitted by Caspar, or like by someone who like knows a little bit about this literature, you just have like a very high credence that like if you face a CooperateBot, probably something funny is going on, right?
Yeah.
You have a high credence that there are like some simulations being run of your program that check what your program does against various opponents, and so you have to optimize for that case much more than you optimize for the case where your opponent is just a CooperateBot. Whereas with the water bottle, you don't really have this, right? I don't know why would someone simulate like, okay, the water bottle could have been.
I mean, people really did design this water bottle by thinking about how people would use it, right? So like, if I'm I think I have a few thoughts there. Firstly, like, if I'm just naively like, did people change how this water bottle would work depending on how other people would like interact with it? Like that's just true. I mean, they didn't get the water bottle itself to do that, so maybe that's the thing I'm supposed to check for. It's also true that like, if you do go to real, and maybe this isn't like a great example because, so if you go to real like iterated mutually transparent prisoners dilemmas, right? Like people do actually just write dumb programs in those. And it's possible that like, okay, these are played for like $10 or something. And that's why people aren't really trying. But in fact, like, some people are bad at writing these programs.
Yeah.
And you want to exploit those programs, right?
Yeah.
And I guess I also have this issue, which is like, okay, so it seems like then what's going on is like my overall like program strategy or something is first check if I'm in a situation where I think the other program was designed to like be, designed to like care about what I am going to do, then cooperate, otherwise defect. Maybe this is not so bad in the simulation setting. In the proof-based setting, this would be pretty bad, right? Because now it's like much harder to prove nice things about me. In the simulation setting, it might just be fine as long as we're really keeping everything the same. Yeah, maybe this is an advantage of the simulation setting, actually. I don't really know.
Yeah, sorry, I'm not sure I fully followed that.
Okay, like, I took your proposal to be, okay, like, the thing you should do is you should, like, figure out if you're in a strategic setting where the other person is, like, basically definitely not going to submit a CooperateBot. Mm-hmm. Where I'm imagining myself as the computer program. Mm-hmm. And maybe this is, like, kind of different to what you were saying. But I was imagining that the program was check if the other person is going to, check if the other computer program was plausibly strategically designed. Then, yes. If so, then do ϵGroundedπBot, otherwise do defectBot. And there's a concern that, like, for example, one concern is like different people write their programs to do this check in different ways, and they end up like one of them ends up being wrong. Maybe this is not a huge issue. I don't know. It feels like it adds complexity in a way that's like a little bit sad.
I could imagine that, I guess for the proof-based ones, the challenge is that they need to be able to prove about each other that they assess whether they're in a strategic situation.
Yeah.
Like they need to assess this consistently or something like that.
Yeah, yeah. Well, also, the more complicated your program is, the harder it is for other people to prove stuff about you. And so you like one thing you kind of want to do if you're a proof-based program in a world of proof-based programs is like be relatively easy to prove things about.
Yeah.
Well, depending on how nice you think the other programs are, I guess.
Yeah. Yeah, I guess for example, in the, like you brought up the tournament case, and there, like, I mean, in practice, I think, yeah, you should, in the tournament, you should, for various reasons, you should mostly try to exploit these, like CooperateBots, or like these, like, just programs that are just written by people who have thought about it for 10 minutes or who just don't understand the setting or something like that. Like, in part because, I don't know, like you shouldn't, I don't know, you wouldn't expect people to submit this, like, this cooperation bot hierarchy thing because there's just other things to do, right? Mm. So So it's sort of like there's just like in some sense there's a higher prior on these kinds of programs. But you could imagine a version of the tournament setting where you're told who wrote the opponent program, and then your program like distinguishes between, you know, someone who has, I don't know, publications on program equilibrium wrote the opponent program, and then you think like, okay, well, all kinds of funny stuff might be going on here. Like I might currently be simulated by something that tries to analyze me in some weird way, so like I need to think about that. Versus the opponent is written by someone who I don't want to I don't know,
a naive podcaster,
and I I don't know, by someone who just doesn't know very much about the setting. And then maybe there you think, okay, most probability mass, like most kind of prior probability mass, is on them just having screwed up somehow, and that's why their program is basically a CooperateBot. Which I think probably like in these tournaments I would imagine that like, I don't know, 30% of programs are just something that just fundamentally doesn't work, doesn't do anything useful, just, I don't know, checks whether the opponent has a particular string in the source code or something like that. And meanwhile, very little probability mass on these sophisticated schemes for like check whether the opponent cooperates against CooperateBot, like in a way that's useful. There is, so I guess, so we talked a little bit about like how, like whether, to what extent it's desirable to exploit CooperateBots. There's then also the question of like how exactly to do this. Here's one more thing on this question of whether whether you need to kind of like know like whether the opponent is part of the environment or strategic, which is that you can think about like the repeated prisoner's dilemma, right? And there, like, I mean, tit for tat, you know, everyone agrees it's a reasonable strategy. And tit for tat also cooperates against CooperateBot. Right. And I suppose there, like, I would think there it's sort of analogous, that you need to, like, tit for tat is a reasonable strategy if you think that your opponent is quite strategic. And the more you're skeptical, the more you should, I don't know, maybe you should just be DefectBot, right? Like against your water bottle, maybe you can be DefectBot. And then there's like some kind of in-between area, right, where you should do tit for tat, but maybe in round 20 you should try defecting to like see what's going on. And then if they defect, you can maybe be pretty sure that they're that they're strategic.
I guess like it seems to me like the thing you want to do is like you want to have like randomized defection, then like see if the opponent punishes you, and then otherwise do tit for tat, but also be like a little bit more forgiving than you otherwise would be in case other people are doing the same strategy.
I guess one difference between the settings is that you can like try out different things more. Which I think also leads nicely to the other point, which is like how exactly would you do this, like punishing exploiting CooperateBots. So I do think one kind of just like a fundamental difficulty in the program equilibrium setting for exploiting CooperateBots is that it's sort of like, aside from like kind of little tricks, it's difficult to tell whether the opponent is sort of a CooperateBot in the relevant sense, right? Like intuitively, what you want to know is like, if I defected against my opponent, would they still cooperate? And if that's the case, you would want to defect, right? But this is sort of like, this is some like weird counterfactual, right? Where we like, where you have all of these usual problems of like conditioning on something that might be false. And so you might get all kinds of weird complications. So I think like in comparison to the tit for tat case, where I mean, it's not clear what exactly you would do, right? But maybe in some sense you can try out against a given opponent. You can try out sometimes defecting, sometimes cooperating, and seeing what happens. There's sort of there's less of that in the program game case, because you're one program, there's some action that you play. You can think if I played this other action, but it's sort of like it's a weird. You get these typical like logical run into these typical logical obstacles.
Although it feels like it might not be so bad. So like imagine I have this thing where I'm saying, okay, suppose I defected. Would you then would you cooperate against a version of me that defected? If so, then I'm going to defect. And like and in that case, it seems like my defection is going to show up in the cases in which you would cooperate, and therefore, that counterfactual is like not going to be logically impossible, right?
Yeah, that's a good point. Yeah. So so I guess that's like a very natural extension of, let's say, these proof-based bots.
Yeah.
Is okay. What if you first try to prove if I defect, the opponent will cooperate.
Yeah.
This will defect against CooperateBots, which is good. The question is whether this will still. What does this do against itself? It can't. Yeah, this will still cooperate against itself, right?
Yeah, because it can't like if I'm asking, will you cooperate if I defect? The answer is no if I'm playing myself, because I always have to do the same thing as myself because I'm me.
Yeah, maybe this just works.
I bet there must be some paper that's checked this.
Yeah, I'm now also even trying to remember, because there is one of these proof-based papers, they do consider this like prudent bot.
Yep.
Yeah, which does something much more kind of hacky. Of like, it tries to prove, and there's some like logic details here. It tries to prove that. Okay, there's one issue with the program that you just described that I just remembered. But let's go to prudent bot first. So prudent bot just checks whether you would cooperate against defect bot. And then if you cooperate against defect bot, I can defect against you.
Right.
I don't know. To me, this is sort of like a little bit like, I mean, it's natural to assume that if the opponent cooperates against defect bot, they're just like non-strategic. They haven't figured out what's going on.
Yeah.
And you can defect against them. But like, in some sense, like, this is quite different from this, like, does my defection make the opponent defect or something like that?
Yeah,
right?
like it's both the wrong counterfactual and it's like a little bit less strategic, right?
Yes. Yeah.
Yeah.
The things that I'm aware of that people have talked about are more like this, where they check these like relatively basic conditions, which like you can view them as sort of checking for specific kinds of corporate bots. Like I guess another thing you can do is like for the ϵGroundedπBots, right?
Yeah.
Just add in the beginning a condition if the opponent is just a corporate bot, or like if the opponent never looks at the opponent's source code at all. You can defect against them. Like you can add these sorts of things, and like I think from the perspective of like winning a tournament, you should think about a lot of these sorts of conditions, and try to exploit them to defect against as many of these players as possible. But it never feels that sort of like, it's not really satisfying. It feels sort of like a kind of like a trick, or like, I don't know, some hacky thing. Whereas the thing you proposed seems more principled. Okay, now on this thing, I could imagine like one issue is that to prove, like when this program faces itself, it first needs to prove like I need to prove that if I defect, like basically I need to prove to like I think so. One problem is always that you need to sometimes, to analyze opponent programs, you need to prove that some provability condition doesn't trigger. And the problem is that just from the fact that you think this condition is false, you can't infer that it's not provable because of incompleteness. So I could imagine that like I can't prove that your program doesn't just falsely prove that your program can safely defect against me.
Yeah.
Because like you might think, well, it might just like sort of like I like when I prove things, I don't know whether whether piano arithmetic or like whatever proof system we use, whether it's consistent.
Right.
And so there's always a possibility that kind of like every provability condition triggers, which means that I don't know whether your first condition triggers. There is, so actually for this prudent bot, this also arises, right? Like for, like if I am this prudent bot, so I try to prove, I first try to prove whether, or like as part of my analysis of your program, I try to prove that you would defect or like cooperate or whatever. Like I try to prove something about what you would do against DefectBot, yeah. And for that, if you're, let's say you're just this like basic, some more basic like Löbian fairbot type structure, then in my analysis of your program, I need to conclude that you're like, that your clause that if I cooperate, the opponent does cooperates, or like your clause, like if I can prove that the opponent cooperates, I need to conclude that this won't trigger. Like to prove that you don't cooperate against DefectBot, I need to conclude that you won't falsely prove that DefectBot will cooperate against you.
Okay.
Which means that, and this I can't prove in PA, like in piano arithmetic, like or in the same proof system that you use. So what they actually do for the prudent bot is that I need to add to, like I need to consider, I mean they call it PA plus one. I don't know how widely this is considered. Like I need to consider piano arithmetic or like whatever proof system I use, plus the assumption that that proof system is consistent, which gives rise to a new proof system, which can then prove that your if condition is not gonna trigger. And so, yeah, so this is some general obstacle.
Right, and we've got to sort of coordinate on what proof systems we use then, because if I accidentally use a too strong proof system, then you have difficulty proving things about me. And I guess it's also like this thing about, well, if I defected, would you still cooperate with me? It feels a little bit hard to like in the proof-based setting, I can say like, you know, if my program on your program outputted defects, would your program on my program output cooperate? Like I could just like do that conditional or whatever. If I want to do this in like a simulation-based setting, which I think there are reasons to want to do, right? Like sometimes you just can't prove things about other people and you have to just simulate them. And it's kind of nice because it's like moving a bit beyond like strict computer programs. It's also nice because like maybe it's hard to prove things about neural networks, which was one of the motivations, right? But like, I don't even know what the condition is supposed to be in that setting. Like maybe if we're like stochastic programs, I could say like, okay, like condition, like maybe I could do like a conditional on like this stochastic program outputs defect, but it's not even clear that that's like the right thing, because like you're looking at my program, you're not looking at the output of my program.
Yeah, though you can have programs that do things like if the opponent cooperates with probability at least such and such. I think that is like one can make those kinds of things well defined at least.
Yeah, but like if my program is like somehow what I want to say is if you cooperate with, I don't know, with high probability against a version of me that defects, you know what I mean? Like either you're simulating just a different program or you're simulating me, and I don't know how to specify you're simulating a version of me that defects. You know what I mean?
Yeah, I agree that's
yeah. In some special cases, maybe I could like run you, and if I know what location in memory you're storing like the output of me, I can like intervene on that location of memory. But it's A, this is very hacky, and B, I'm not convinced that this is even the right way to do it.
It's, I think, there's, I guess there are like sort of various settings where you constrain the way that programs access each other that would allow more of these counterfactuals, right? Like you could, for example, you could consider like kind of like pure simulation games where you don't get access to the other player's source code, but you can run the other player's source code. And I guess in those cases, some of these counterfactuals become a bit more more straightforwardly well defined, right? That you can just
Right.
like, what if like when I just replace every instance of your calls to me with some action?
Yeah.
There's some I mean, there's some papers that consider these like this like more kind of like pure simulation based setting as well. But yeah, it's obviously that would not allow for like proof-based stuff and things like that.
So, okay, I think at this point I want to tee up your next paper. So, in particular, in this paper, there are two types of strategies that you like can't turn into this like program into the program equilibrium setting, right? So, I think we already discussed win, stay, lose, switch, where I have to like look at what you did in the last round, and I also have to look at what I did in the last round. There's also this strategy in the iterated prisoner's dilemma called grim trigger, where like if you've ever defected in the past, then like I'll start defecting against you, and if you've always cooperated, then I'll cooperate. And neither of these you can have in your like ϵGroundedπBots. Why is that?
Yeah, basically the main constraint on these ϵGroundedπBots or PyBots or whatever is that they just can't run that many simulations, right? You can run kind of like, I don't know, one simulation with high probability or something like that. Maybe you can do with low probability, you can maybe start 2 simulations or something like that. But the problem is just like as soon as you simulate the opponent and yourself or like multiple things like and like with high probability, you run into these infinite loop issues again that this epsilon condition avoids.
Right.
Like another case is like if you have more than 2 players, things become weird, right? Like if you let's say you have 3 players, intuitively you would want to simulate both opponents, and then if they both cooperate, you cooperate. If one of them defects, then maybe you want to just play the special punishment action against them, like depending on what the game is. But you can't simulate both opponents, right? Like because if you every time you're called start 2 new simulations or even like 2 minus epsilon or something like that in expectation, you get this tree of simulations that sort of just expands, and occasionally some kind of simulation path dies off, but it kind of multiplies faster than simulations hold.
Right. Yeah. Like basically you're doubling, like when you grow, you're doubling, and but you like cut off a factor of epsilon, but epsilon is smaller than a half, and therefore you grow more than you shrink, and it's really bad. And if epsilon is greater than a half, then you're not really like simulating much, are you?
Yeah.
So how do we fix it?
Okay, so we have this this newer paper where I'm fortunate to be the second authors, and first authors Emery Cooper and then Vince Conitzer, my PhD advisor, is also on the paper. So this fixes exactly these issues. And it's I think it's a clever kind of interesting idea. So for this to like explain this idea, we need to imagine that the way that programs randomize works like a particular way, like in a sort of like the architecture of the programming language has to be like a particular way to explain this. So like I guess I don't know, if you like have like a normal programming language, like I don't know, you call like random.random or like some such function, and you get a random number out of it. But another way to model randomization is that you imagine that sort of like at the beginning of time, or like when your program is first called, it gets as input an infinite string of random variables that are like rolled out like once in the beginning, and then you have like this long string of like, it could be, for example, bits, and all you're gonna do is like use the bits from this input. And so in some sense, like this is sort of a way of modeling kind of randomization with a deterministic program. Like in some sense, randomization is like running a deterministic program, well, on an input that is random, right? You have as part of your input, you get this random string. And so let's imagine that you get these as a random string as input, but each entry is just a random number between 0 and 1. The way that these like infinite simulation issues are fixed is that when I run, for example, like my two opponents and myself, I pass them all the same random input string, and that way I sort of like coordinate how they halt, or like at what point they halt. So like very specifically, here's how it works. So let's maybe first consider a version where you just, the issue is just that you have multiple opponents, but you're still doing this something like ϵGrounded pBot, where you're happy to look just as at the last round, and maybe win. Win, stay, lose, shift, where you maybe also look at your opponents or at your own previous action. So what you do is you look at your random input string, and if the first number is below epsilon, then you just immediately halt in the way as usual by like just outputting something.
Yeah.
And otherwise, you remove the first thing from this infinite input, like random input string.
Yeah.
And then you call all of these simulations, like you simulate like both opponents, let's say like you have two opponents and yourself, with the first entry in that list removed.
Yeah.
And now how does this help? Well, I mean, the opponents might do the same, right? Like, let's say they all check like the first thing, check whether it's smaller than epsilon, and then remove the first and call recursively. Well, the trick is that by all of them having the same input string, they all halt at the same point, right? All your simulations are going to halt once they sort of reach the specific item in this input string, like the first item in this input string that is smaller than epsilon.
Yeah.
And so that allows for, simulating multiple opponents. You can also, you can simulate yourself, of course. And you can also simulate like multiple past time steps by instead of passing them just the input string with the first thing you removed, you can also check like what did they do like in some intuitive sense, like kind of 2 time steps ago, by removing the first 2 random variables from your input string,
right,
and passing that into them. So this is the basic scheme for making sure that these simulations all halt despite having a bunch of them.
My understanding is that you have like 2 constructions in particular. There's this like correlated one and this uncorrelated one. Can you give us a feel for like what the difference is between those?
Yeah. So there are differences in the setting. So the correlated one is one where you get a correlated, or like you get a shared random input sequence.
Right.
So I know, like you could imagine that like we all get there's some central party that generates some sequence of random numbers, and it just gives this sequence of random numbers to all the players, and so they have the same random sequence, and then maybe additionally they have a private one as well, but they have this shared random sequence. And then in this shared setting, basically all the results are much nicer. It's like we get nice results in the shared randomness setting, and mostly more complicated, weird results, or like also, I mean, in some cases we also just can't characterize what's going on in the non-correlated case. But in the correlated case, we specifically propose to use the correlated randomness to do these recursive calls. So I use when I call like my 3 opponents and or 2 opponents and myself on the last round, I take the shared sequence of random numbers, I remove the first, and call the opponents with the remaining one, rather than using the private one. And then in the case where there is no shared randomness, we just use the private randomness instead. So in some sense, it's sort of like it's almost the same program. I mean, there's some subtleties, but it's like in some sense sort of the same program, and the main difference is that, well, you feed them this randomness that's
you're giving the other
randomness.
person your private randomness, right?
Yes. Yeah. I'm giving. Yeah. I mean, I don't have access to their randomness. I have to give them my randomness, which also, like, I mean, maybe it's not that hard to see that this is like you get like somewhat chaotic outputs, right? Like in some sense, my prediction of what the opponent will do is sort of like in some sense is like quite different from what they're actually going to do. Because they might have like very different input.
Right. Which is an interesting, like in some ways it's an interesting, like it's maybe more realistic that like I get to sample from the distribution of what you do, but I don't get to know exactly what you will actually do, right?
Yeah.
Maybe this is just me restating that I believe in private randomness more than I believe in public randomness. So here's one thing that I found, like, okay, here's a thing that I believe about this scheme that strikes me as kind of sad. It seems like so basically you're gonna use this scheme to come up with things like these epsilon grounded fair bots, and they're gonna like cooperate with each other. But like reading the paper, it seemed like what kind of had to happen is that all the agents involved had to kind of use the same sort of time step scheme, right? Like at least in the construction, it's like, oh yeah, they're both like, everyone has this like shared sequence of public randomness, so they're both waiting until like the random number is less than epsilon, and that at that point they like terminate. And I'm wondering, like strong degrees of, so I guess I'm seeing this as like, okay, in the real world we do have public sources of randomness, but there are a lot of them. It's not obvious which ones they use. It's not obvious like how to turn them into like, is it less than epsilon, or so like it seems really sad if the good properties of this have to come from coordination on the scheme of, we're going to do the time steps and we're going to do it like this. But I guess I'm not sure like how much coordination is really required for this to work out well.
Yeah, that is a good question. I mean, I do think that this is sort of like a kind of price that one pays relative to the original epsilon grounded PyBots, which obviously don't have these issues.
Yeah.
I think it's a little bit, I don't know, it's a little bit complicated, like how robust this is exactly. So the results that we have, like we have this result, this folk theorem about what equilibria can be achieved in the shared randomness case by these kinds of programs, and it's sort of like the same as for repeated games, also the same as for like these syntactic comparison based ones. So like everything that's better for everyone than their minimax payoff, like the payoff that they got if everyone else punished them.
Yeah.
Like some of these characterizations, or like the fact that it's an equilibrium obviously means that it's sort of robust to all kinds of deviations, but like like getting the equilibrium payoff, that requires coordination on these random things. We also, like, another thing is that, like, I don't know, maybe this has already been kind of implicit or like kind of explicit, I guess, in the language I've used with these time steps. Like there's a close relation between this and repeated games. Like now it's really just sort of like full repeated game strategies.
Yeah.
And this whole like relation to repeated games hinges on everyone using basically exactly the same time step scheme. Like basically if everyone like uses the same epsilon and they do the cutoff, like if the same source of randomness is like below this epsilon, then it's in some sense it's all exactly like playing a repeated game with a probability of epsilon of terminating at each point, and it's sort of like there's a very nice correspondence. So some of the results do really like fully hinge on like really like exact coordination on all of these things.
Yeah.
But there's also like there's some robustness still. Like it's so for example, the programs still halt if someone chooses like a slightly different epsilon.
Yeah.
If someone chooses a different epsilon, like the relationship to repeated games sort of goes away, right? There's like it's hard to think of like a version to play a repeated game where everyone has like their separate like cutoff probability. I don't know, maybe one can somehow make sense of this, but it's like it does become like kind of different from that. But let's say I choose an epsilon that's like slightly lower. Well, we're still going to halt if like at the point where we find an input where everyone's we find a point in this random sequence where it's below everyone's epsilon, right?
Yeah.
So like some people like choosing slightly different epsilons is like it makes like it becomes harder for us to say what's going on, right? We can't view it as a repeated game anymore.
Yeah.
But it still works. It's not like everything immediately breaks in terms of like everything not halting or something like that.
Yeah, or even if you're using if I'm using one public random sequence and you're using another, like even if it's like uncorrelated, it seems like as long as I eventually halt and you eventually halt, it's not going to be too bad. And,
in particular, we're gonna halt at the point where like both of our sequences have like the halting signal, right?
Yeah, and it also seems like I guess like it sort of depends a little bit on what our policies are, but it seems like as long as I'm not like too picky, like as long as I'm not like super specific about like what exact sequence of cooperates and effects I'm sensitive to, like surely it'll like maybe it'll just be fine even if we're like not super tightly coordinated.
Yeah, like I mean, I guess here again, it's sort of like this, like trying to kind of import our intuitions from repeated games that I guess there's like a game theoretic literature about that we maybe also have like experience from like daily life. I guess if you like in practice play a repeated game, you're not gonna play an equilibrium. You're gonna play something where like you do something that's like sort of trying to go for some compromise. Maybe the other player goes for some other compromise, and then you kind of try to punish them a little bit or something like that, right? Like and I would imagine that there's a lot of this going on in this setting as well.
Yeah. So okay, I think I'm maybe a little bit less concerned about the degree of coordination required. I think like so there are two other things about this paper that seem pretty interesting. So the first is just like what the limitations on the equilibria you can reach are. And my understanding is that like you can characterize them decently in the correlated case, but it's pretty hard to characterize them in the uncorrelated case. Or can you explain to me and my listeners just what's going on here?
Yeah, so in the correlated case, it really is quite simple. I mean, I don't know. They're like, as always, there are like some subtleties, right? Like you need to specify, for example, what exactly are you going to do if you simulate some other player and they use their private signal of randomness, right? Which they're not supposed to do in some sense. Well, you need to somehow punish them, and the people above you need to figure out that this is what's going on. So there's like some of these sorts of subtleties. But I think basically there is just like a very close relationship between these programs and the repeated game case. So it is just basically like playing the repeated case, and like even deviation strategies you can view as playing the repeated game by saying like, well, if they get like this random string as input that has like 10 variables left until they get to the below epsilon case, then you kind of can view this as them playing a particular strategy at time step 10.
Well, hang on. The what do they do with the access randomness? So my recollection, which might be wrong, was that you punish people for accessing like other people's private randomness, but I thought they could still access their private randomness.
I think you do have to, I think, punish people for using their private randomness.
Okay.
And then the complicated thing is sort of that like I might simulate you, and you might simulate a third party, and the third party uses their private randomness, and now you as a result punish them, and then I now need to like figure out that you're just punishing them because they use their private randomness,
and you're not punishing me.
I don't know, like
So that condition seems kind of hard to coordinate on, right? Because like naively you might have think, well, it's my private randomness, it's my choice, you know?
Oh, the condition to punish private randomness. This I think this is a reasonable point. Maybe one should think about ways to make this more robust to this. I guess it's sort of like yeah, I mean, one has to think about like what exactly the game is and like how much harm the private randomness can do, right? Like if
Yeah.
in some cases it doesn't really help you to do your own private randomness, and then maybe it doesn't. I don't need to punish you for it, but like if you have like I don't know, if you can, I don't know, there's like there are like 20 resources and you can steal them, and you're gonna randomize which one you steal from, and the only way for us to defend against this is by like catching you at the specific resource or something like that, then maybe we do just need to think like, okay, as soon as there's like some randomness going on, it's like a little bit fishy.
Yeah.
But yeah, like you could imagine games where you wanna allow some people to randomize privately, or like use their private randomness for like, I don't know, choosing their password. Maybe this is sort of like a fun example. Like if you like at time step 3 you need to choose a password, and like in principle the way our scheme would address this is that we all get to see your password, or like we like in some sense we get to predict how you use your password.
Yeah.
I mean, it's also still important to keep in mind that like these past time steps are things that don't actually happen. So like we predict what you would have chosen at time step 3 if time step 3 was like the real time step, but nonetheless, if you like the way our scheme would, like, you might think, okay, if you have to choose your password with the public randomness, then we all know your password, and doesn't this mean that we all would want to log into your computer and like steal your stuff? And the way the scheme would address this, I guess, is just that, well, everyone, like, someone could do that, but they would then be punished for this.
Or maybe they do it, and it's just like, well, that's the equilibrium we picked. Sorry.
Right. It could also be. Yeah. It could also be part of the equilibrium. Yeah. That's also true.
Yeah. So okay. So in the correlated case, it's like basically you have like a folk theorem, and there's something about just like things that are things that you can punish people for deviating from. That's like basically the equilibrium you can reach.
Yeah.
Roughly. Okay. And then I got to the bit of your paper that is about the equilibria you could reach in the uncorrelated game, and I'm gonna be honest. So earlier we had a recording where we were going to talk about these papers, but actually I got like really bad sleep like the night before I was supposed to read the papers, and so I didn't really understand this characterizing simulation based programming equilibria paper. It was like beyond me. This time, I had a good night's sleep. I was rested. I was prepared. And I read this paper, and then like once I get to the like limitations on the equilibria of the uncorrelated one, that's where I gave up. Like the theorems did not make, like, I understood each of the symbols, but I didn't get what was going on.
Yeah.
Is there a brief summary of what's going on, or is it just like, well, we had to do some math and that turns out to be the condition that you end up needing?
Yeah, at least for the purpose of like a very audio focused format, I think it's probably one can't go that much into the details of this. I think one can explain a little bit why one doesn't get a full folk theorem in the uncorrelated case. Like I think there are some relatively kind of intuitively accessible reasons for that.
Yeah. Okay, let's start there.
Okay, let's start there. So the problem in the uncorrelated case is basically that, like, let's take like a 3-player case.
Yep.
Like we are 2 players, and there's like a third player, Alice, and now there's the question, like we want to implement some equilibrium, right? And now there's a question: can Alice profitably deviate from this equilibrium?
Yep.
And now the issue is Alice can use her like private randomization in some ways. And now, so the problem is basically that us catching her deviation is uncorrelated with her actually deviating in the actual situation. And additionally, whether I detect her deviating is uncorrelated with you detecting her deviating.
Okay.
And this all makes punishing, especially like punishing like low probability deviations, very difficult. So for example, if like if Alice just like with some small probability that she determines with her private randomness, she defects in some way, right? Then okay, in the real world, like for her like actual action that will determine her utility, there's this small probability that she'll defect, and then there's some probability that like our simulations of her, which we're running like a bunch of, there's some probability that we'll detect these. But because like when I simulate Alice, I simulate her like with a completely different random string than the string that Alice has in the real world, right? So in some sense, I can't really tell whether she's actually going to deviate. And then also like you're going to simulate Alice also with your private randomness, which means that like whether in your simulation Alice defects is also uncorrelated with whether she defects in my simulation.
Wait, so first of all, I thought that even in the correlated case, like whether she defects in simulation is different from whether she deviates in reality, because we cut off the private round. We get rid of the first few random numbers and then like run on the rest, right?
Yes, that is true. I guess the
thing where we disagree, like that seems like important and different.
So maybe that's I'm also not sure about the other one now, like how it, but like I think the other one is more straightforward. We can't like it might be that to punish her deviating we both need to do a particular thing, and we just can't, like we'll both. So I mean there's also, so like it's a little bit complicated, right? Because you might think like, well, we can simulate Alice like for a lot of time steps, right? So we don't, like you might think that even if she defects with like low probability, well, we're simulating her a bunch in some way. And so there are like some complications here, they like she needs to deviate in some like relatively clever way to make sure that we can't detect this with high probability. So it is all a little bit complicated, but I think this like we can't correlate our punishment, or like we can't even correlate whether we punish, and so like if like her defecting requires, like if the only way to get her to not defect is for both of us to at the same time do a particular action, that's sort of difficult to get around.
Okay, here's a story I'm coming up based on some mishmash of what you were just saying and what I remember from the paper. We're in a 3-player game, right? Therefore, punishing actions, firstly, they might require like a joint action by us two, and therefore like that's one reason we need us to like be correlated on like what Alice actually did, at least in simulation. Another issue is like, suppose I do something that's not in the good equilibrium and you see me doing that. You need to know whether I did that because I'm punishing Alice or whether I was the first person to defect. And like in that, like if I'm the first person to defect, then you should try punishing me. But if I'm just punishing Alice, then you shouldn't punish me. And so like if we in our heads see different versions of Alice, like if you see me going away from the equilibrium, you need to know whether that's because in my head I saw Alice defecting, or if it's because in my head I thought I want to defect because I'm evil or whatever. I don't know if that's right.
Yeah, I'm not sure whether that is an issue, because like when I see you defecting, it is like because I simulate you with my randomness as input. And then you see with my randomness as input. Alice defecting like one level down.
Okay.
Which means that I like remember that I'm also like I'm simulating like kind of all of these past time steps as kind of determined by my randomness.
Okay.
So I think I can see whether the reason you defect in my simulation is that you saw Alice defect.
Okay. Wait, if we're using the same randomness, then why isn't the case that we both see Alice defect at the same time with our same randomness?
So I mean, this is all like my simulation of you, right? Rather than the real you.
So the real we's might not coordinate on punishment.
Yeah. So yeah, I mean this is sort of like another thing that's like,
Oh, okay.
like even I guess even with the like very basic epsilon grounded PyBots, you can kind of like imagine they play like in their head they're playing this like tit for tat where like it's going back and forth, and like one person does this based on their randomness, and then the other person sees this and then responds in some particular way.
Yep.
But if you don't have shared randomness, all of this like this is all like complete fiction, right? You haven't like actually coordinated with the other player and like seen back and forth. Like, so it might be that like I run this simulation where you detected Alice is defecting, and then I also defect on Alice, and then we're like happily like defecting on Alice, and like we're in the simulation, we're thinking, yeah, we're doing so well, we're like getting this Alice to regret what she does and so on. But the problem is that you run a completely different simulation. So like you're in your simulation of what Alice and I do, you might see everyone cooperating, and everyone thinks like, oh, everything's great, we're all cooperating with each other. And then we've done the simulation, and now we're playing the actual game, and I defect thinking like, oh yeah, we're on the same team against Alice, and then you think like, oh nice, we're all cooperating, and you cooperate, and then we're like landing in this like completely weird outcome that sort of like doesn't really happen in the simulation. It's like sort of unrelated to what happens in the simulation.
Right. So Alice basically says, hey, I can get away with like doing nasty stuff because like they won't both be able to tell that I'm doing the nasty stuff, and therefore I won't properly be punished. Like in the real world. And so these gnarly theorems, should I basically read them as like the preconditions are there's some math thing, and the math thing basically determines that like this kind of thing can't happen, and those are the equilibria you can reach. Is that it?
Yeah, so I think one thing that drives a lot of these characterizations is sort of this like, yeah, Alice can like defect with like low probability. I think usually that's sort of like the more problematic case, is that she defects like in a particular kind of clever way with low probability, which means that like we're very unlikely to both detect it at once.
Yeah.
I think that is driving these results a lot. But yeah, there is like to some extent. I mean, you said this earlier. Like, well, there's some math going on. Like, I think to some extent that's true. There is. So I think one thing that I liked about these results, despite like yeah, I mean, it is of course one prefers results that are like very kind of clean and simple, like the Fock theorem, where you just have this very simple condition for what things are equilibria, and like yeah, our characterizations are mostly these are kind of like complicated formulas. I think one thing I like is that for some of these characterizations, one can still kind of hold on to this interpretation of there being time steps, and like you simulate what people do at previous time steps and things like that, which sort of like it's sort of very intuitive that this works for the case where everyone kind of plays nicely with each other and everything is correlated, and like in some sense we're playing this mental repeated game where we all use the same randomness, and so we're all playing the same repeated game, and really it's just the thing that is sampled is like which round is the real round. It's sort of clear that the time step story works, and it's sort of it's nice there that like I don't know, there are like some results where you can still like use this time step this time step picture. So that's like one kind of nice thing about the results. But yeah, it is unfortunately much more complicated.
Fair enough. And then so another part of the paper that is kind of cool and that you foregrounded earlier is it has this definition of like simulation-based programs. And so earlier you mentioned there was a definition of like fair programs or something, which I guess like maybe you were referring to this definition.
Yes. We do have, so like in some sense the paper has like three parts, right? It's the one with the correlated case with the epsilon grounded, like these generalized epsilon grounded PyBots that pass on the shared random sequence, and then the uncorrelated case with the epsilon grounded fair bots. And then we also have a section that kind of analyzes more general simulationist programs, which are programs that just intuitively all they do is like run the opponent with themselves and the other players as input. That has this definition, and then we have like a characterization as well. Like for example, one result that we also show is that in general, like general simulationist programs are more powerful at achieving equilibria in the uncorrelated case than the ϵGroundedπBots. Like I'm not quite sure how much to go into detail there, but like one intuition that you can have is like in the ϵGroundedπBots, like to some extent, sort of like everyone has to do the same thing, whereas you could have settings where, I don't know, only I need to do simulations, and then if only I simulate your program, I can like run like 10,000 simulations or something like that. And like this is something that obviously the ϵGroundedπBots can't do. Like you can't just independently sample 1,000 responses from the other player. And this we do there have this this definition of simulation as programs. I'm not sure I remember the details off the top of my head,
but it's some recursive thing of like you've got it's a simulation program is like it calls its opponent on a simulationist program, which maybe includes itself, and maybe I forget whether it explicitly has like ϵGroundedπBots as a base case or something. Or maybe simulating nobody is the base case. Or just ignoring the other person's input.
I think so. I think that's also coming back to me. I think it's like something like that. I think that the tricky part is that you can, like, maybe intuitively you might think that a simulationist program is just one that like calls the other program with some other program as input, but then if you don't constrain the programs that you give the other player as input, you can sort of smuggle this like non-behaviorism back in by having like, I don't know, what does my opponent do against these like syntactic comparison bots or something like that,
right? There's a good appendix, it's like, for why we do it this way, see this appendix, and then you read the appendix, and it's like, oh, that's like pretty comprehensible. It's not one of these cases where the appendix is all the horrible, like, crazy stuff.
Glad to hear that you like the appendix. Some of the appendix is also just very, very technical, like working out the details of.
I skipped those appendices, but there are some good appendices in this one.
Nice.
All right, the next thing I want to ask is what's next in program equilibrium? What do we like? I don't know what else do we need to know? What should enterprising listeners like try and work on? Or is there any work that's so? Earlier I asked you like about what was the state of the art like before you published robust program equilibrium. Like, is there any like work coming out at around the same time, which is like also worth kind of talking about and like knowing a bit about the results of?
So I think there are a bunch of different directions. So So I do think that we still leave open like various sort of technical questions, and there are also like some kind of technical questions that are still open for the for these Löbian programs that it would be natural to answer. So one thing, for example, is that like I would imagine that, okay, maybe sticking closely to our paper first, there are some like very concrete open questions like even listed in the paper. Like I think it's not clear whether, okay, I'm not entirely sure, but I think like in the 2-player simulationist program case, it's not clear whether, for example, all Pareto optimal better than minimax utility profiles can be achieved in simulationist program equilibria.
Okay.
So they're like, I don't like, maybe this is not quite the right question, but like you can check the paper. I mean, there's some also like, I mean, for some of these, like we have some characterizations for these uncorrelated cases, but I think for the general simulationist case, we don't have a full characterization. So if you want to kind of go further down this path of this paper, there are a bunch of directions there that are still after like kind of like little, I don't know, like somewhat small holes to fill in. Then I think another very natural thing is that for like, I think for the Löbian bots there isn't a result showing that you can get the full Folk theorem if you have access to shared randomness, which I'm pretty sure is the case probably even with, like I think probably with with some mixing of like this epsilon grounded stuff and the Löbian proof based stuff, I would imagine you can get basically a full folk theorem, but there's no paper proving that. I don't know.
Sure.
Maybe one day I'll do this myself. But this, I think that's another like very natural question to ask. I think so. In my mind, another like kind of like going a bit further outside of what we've discussed so far. I think in practice, I would imagine that usually one doesn't see the opponent's full source code. And maybe it's also even undesirable to see the whole source code for various reasons. Like you don't want to like release all your secrets. Maybe also like these, I mean, we talked about these folk theorems, right? Like where like everything that is better than this like punishment outcome can be achieved. And this, like, I think game theorists often view this as sort of like a positive result, whereas I have like very mixed feelings about this, because it's kind of like anything can happen, and in particular, like a lot of like really bad outcomes can happen, right? Like, like outcomes that are better than the best thing that I can achieve if everyone just punishes me maximally, right? Like, well, it's not very good, right? Like there are lots of very bad things that people can do to me, right? And like so there are lots of equilibria where I get very low utility, right?
Yeah, and in particular, you've got to like if there are tons of these equilibria, it's like the more equilibria there are, the less chance there is we coordinate on one, right?
Yeah. So I guess one positive thing is that, like, I mean, you have this sort of like, I don't know, like in the correlated case, you have this like convex space of equilibria. So at least it's sort of like, well, you need to find yourself in this convex space rather than finding yourself between like 6 discrete points. And so maybe that makes things easier. But yeah, I think basically I agree with this. I think on our last episode, we this is my second appearance on Axurb, right? On the first episode there was on Axurb, we discussed this equilibrium selection problem, which I think is very, very important and motivates a bunch of my work. So maybe if you have less information about the other player, then you get fewer equilibria. Like in the extreme case, if you get only like very little information about the player, maybe you only get one additional equilibrium relative to the equilibria of the underlying game. And I think we discussed the similarity-based cooperation paper also on the previous episode, and that is basically such a setting. It's like basically a program equilibrium setting where you don't get full. Like you don't get the full opponent's source code, but you get some signal of, like, in particular, how similar the opponent is to you, and there are some results about how you get only good equilibria this way. So I think in general that's sort of like a natural direction to go in. Also, like you can also do like more practical things there, right? Like the similarity-based cooperation paper has some experiments. If you like, you can do experiments with language models. Where, like, in some sense, you also, like, this is sort of true, right? Like, if my program is, I prompt a particular language model, right? And then you know my prompt, but you don't know all the weights of my language model, or maybe you can't do very much with all the weights of my language model. Like that is a sort of partial information program equilibrium. So I think that is another natural direction, and then also I think. I think you drew these connections to like decision theory, right? Which is sort of like, if you, like, in some sense, like if you are the program and you have to reason about how you're being simulated and people are looking at your code and stuff like that, how should you act in some kind of rational choice type sense? Like that's sort of like the problem of decision theory. And in some ways you could view this program equilibrium setting as sort of addressing these issues by taking this sort of outside perspective, right? Like, instead of asking myself, what should I, as a program who's being predicted and simulated and so on, what should I do? Instead of that, I ask myself, I'm this human player who's outside the game and who can write a code, what is the best code to submit? And like in some sense that makes the question less philosophical. And I think like I'm very interested in these more philosophical issues. And I think I don't know, I feel like the connections here aren't like fully settled. Like what like how exactly what exactly does this principal perspective or like this outside perspective correspond to from the person of the agent? Like you said, this equilibrium where everyone checks that they're equal to the other player, like that's an equilibrium where the players the programs themselves aren't rational. They don't do expected utility maximization. They just do what their source code says, right? Yep. So I think this is much more philosophical, much more open-ended than these more technical questions about like what equilibria can you achieve. But I'm still very interested in those things as well.
So the final question I want to ask is, if people are interested in this work, in particular in your work, how should they find more?
Okay, so I just have an academic website. I guess fortunately my name is relatively rare, so if you Google my name, you'll find my academic website.
Yeah.
You can also check my Google Scholar, which I guess has sort of a complete list of my work. I also have a blog where I occasionally post things like somewhat related to these things, like it's related to these kinds of issues. Which is just CasparOesterheld.com.
Yep.
Which in principle should allow subscribing to email notifications. And I also have an account on X, formerly Twitter, which is C_Oesterheld. I think those are probably all the things.
Great, cool. So there'll be links to that in the transcript. Caspar, thanks very much for coming on the podcast.
Thanks so much for having me.
This episode is edited by Kate Brunotz, and Amber Dawn-Ace helped with transcription. The opening and closing themes are by Jack Garrett. This episode was recorded at Far Labs. Financial support for the episode was provided by the Long-Term Future Fund, along with patrons such as Alexei Malafev. You can become a patron yourself at patreon.com/AXRpodcast, or give a one-off donation at ko-fi.com/AXRpodcast. That's ko-fi.com/AXRpodcast. Finally, if you have any feedback about the podcast, you can fill out a super short survey at axrp.fyi.